Hi everyone, welcome to this second video in the electromagnetism scheme of work. This is on a lesson regarding magnetic fields. And this is quite a difficult lesson. It's one of the historical lessons in the schemes of work that you'll have seen before. And the reason for doing a historical lesson on magnetic fields, well, there's two reasons. One is because the field is a really important concept. For understanding magnets and having a sense of how electromagnetism works, and you'll know from if anyone who's taught GCSE physics, all of this stuff, you kind of need to have a sense of what a field is to understand all that left-hand rule business. But it's also important from a physics point of view, in that really appreciating how innovative this idea of fields was is absolutely fundamental for any student who wants to go on and study physics and really get their head around Einstein's theories of relativity. And when we get into quantum physics, and you find out about Dirac and all of these people who they have this picture, this modern picture where actually all matter is just kind of ripples in various fields, and Higgs bosons, all that business. The field is the fundamental concept which everything else in physics has been built on in the 20th century. So this is a really important lesson, but it is quite hard, and to be honest, it's not something that I really understood until very recently. That's one reason, so it's an important concept to introduce. The other is that I think this really humanizes science, because we're going to look at Faraday in this lesson, and his story is really important because he was not educated, he had no mathematical training, and that was actually the reason he was able to make this insight, because everyone else who was part of the elite and had this mathematical training, they were very kind of dogmatically fixed in their ways. And I think that's a really important lesson for all students to say, thinking clearly isn't something that only a certain group of society can do. Faraday's example is a really lovely way of illustrating the virtues of science, which are really looking at the problem as it is, and thinking creatively to try and solve it. So it's a really important lesson, but it's maybe not the easiest to teach. And the way I would start teaching this is by referring back to our guest-deduced check model. So I'd start by writing these three headings, because what we're going to do is show how this concept of the field originated. And what I would tell students is that to understand the field and to understand lots of electromagnetism, we have to go back to before Faraday and think about how scientists understood forces. And the forces that they really understood were the kind of forces that we studied in the last physics units on forces in space. They were forces like this, gravitational forces between the sun and the Earth, like this. Now, hopefully students are pretty familiar with this picture from that unit. The way they understood forces was that, now I've managed to draw that not in a straight line, they understood them as acting in straight lines, always directly between the two objects. Sorry, I've just got to find myself a rubber now. So I'm going to use a ruler actually to make sure I don't mess this up again. But we're going to draw straight lines acting directly between the two objects. I've misplaced my ruler, so I'll do the classic student trick of using a set square. So I'm going to draw this straight line here like this, and straight line here like this. So you could show that this is how scientists understood forces. Now, what they deduced from this picture, because they always thought, okay, they always act in straight lines directly towards the other object. They also had the inverse square law, which we don't need to go into, but the further away it got, as the distance doubled, the force would decrease by 4 and so on. But what you could deduce from this was that if you were to put the sun in the middle of your diagram, and you were to consider the force acting on the Earth here, let's say, and here, and let's say over here, any three random positions, what you would expect is that the force always acts towards the sun, because that's how they understood forces as acting. It would always be two objects, and again, we don't need to go into kind of considering them as point masses and things like that, but basically there were two objects and the force would always act from one object in the direction of the other object. That's how forces work. This is this concept of action at a distance, which was really, really helpful for understanding gravity. And you know, this would be what they deduced from this picture of forces. Well, the check, these were the astronomical observations. Everything we knew about gravitational forces suggested that was true. And all of the orbits and things like that, all of our data said this picture is bang on correct. That's why Newton and his theories were so powerful, because the model he came up with seemed to be confirmed by any experiment anyone could come up with. So what we want to do next is consider a magnet. So let's imagine we've got a magnet here like this. Well, what I'm going to do, I'm going to label that as the North Pole and that's the South Pole. We came across that in the last lesson. And let's imagine these as kind of points like that. Now, if we were to bring a magnetic compass anywhere near that magnet, well, what we'd expect is it's always going to point towards one of the poles. I'm going to show it pointing towards the South Pole, which is foreshadowing what will come later, but yeah, that's fine. The idea is it's always going to point towards one of the poles. And if you were to build on this picture, this is the original picture we had, and it's even the picture we drew in the last lesson. Well, let's imagine we've got the magnet like this. There's the North Pole, there's the South Pole. Again, in this picture, we imagine them just as kind of points. And let's draw three compasses at various points around. Now, if this picture was true, what we'd expect to happen is, well, if we put the magnet here, the compass here, well, we'd expect it to point downwards. If we put it here, we'd expect it to point towards the South Pole. If we put it over here, like that, we'd expect it still to point towards the South Pole. Now, what I would do then in this lesson, what I would show to students, and we'll do this more formally in the next lesson of the scheme, but what I would do here is actually get a bar magnet and get your compasses and show them what you'll show them more formally in the next lesson, but just in really simple terms, do this experiment. And what you want to show them is, okay, if you put the magnet there, and let's put the North and South Pole here, the compass there, then yes, it does point towards the South Pole. But if you put the compass here, well, it might point somewhere like that, not towards the South Pole. And if you put it over here, it almost seems to point parallel to the bar magnet. Definitely not towards the South Pole. So this is really, really strange. And what you want to illustrate by this is that this guess about the nature of forces, that they always act in the same direction as the other objects that is kind of attracting them, that guess is not correct. So where this check, this experiment, all the data we had supported this view, well, even a really simple demonstration, like this one that we can do in class, shows that this guess, that forces always just act in the direction of the other object, isn't quite correct. Now what I'm going to do is then show them what Faraday did. And Faraday had this idea that actually there must be something called a field. And that's a little bit different to the picture of forces that we had before, and I'll try and explain why. So what I'm going to do is show what Faraday did, which is to sketch what he called lines of force. So if I call that N and that S like this, so you just sketch these lines of force, and again, you'll be familiar with this picture, I'm sure, going like this. Then we can add some arrows like this. They always go from north to south. Again, there'll be more on that in the next lesson when they actually draw this magnetic field pattern properly. But what you want to emphasize to students is that these two guesses, these original two guesses, if I just move my visualizer back up, these were based on the idea of what I'm going to call direct forces. Forces always acting in a straight line between two objects. Direct forces. Now what Faraday did was something different. He imagined forces in terms of these lines of force. And he was able to do this because basically to understand these direct forces you needed to know loads of maths and be able to, you need to have read Newton's Principia and understand everything that Newton was talking about. Faraday, he was a working class boy from London, I think somewhere around Canonbury or somewhere around there. and he worked in a bookbinders, and he just used to read all the books that would get brought in. You might need to explain to them bookbinders. Making books was a complicated business in the Victorian era, so he used to read all these books, and he just got really into science and eventually worked his way up and was allowed to do experiments and came up with papers of his own. And he wasn't wedded to this picture because he'd never learned the maths. And he never quite, I suppose, sort of acknowledged how powerful this was. And there was this mindset of scientists that everything had to be explained in terms of this direct forces picture because it had been so powerful in the past. Well, Faraday didn't have that kind of baggage, so he was like, well, I just want to understand it. And again, it's a really nice way of showing what makes a great scientist is someone who's free thinking and able to reimagine everything that's going on. And the real insight that Faraday had was to not think about, okay, what are my two objects, and then add the forces on afterwards. So, okay, my two objects, sun and the earth, magnet and the compass, and so on. He just thought about one object and thought about what does the space in between look like. So he just thought of one object and thought, well, if I were to bring any other object into this around this magnet, in what direction would the force act? And that brings this idea of the field. I think it's a really nice way of illustrating it. And what the field is, and the students will be tested on this in the slides, what they need to understand is that the field shows the direction of the force that would act on a magnetic material that was brought anywhere near that bar magnet. And what's important is that field exists whether or not that magnetic compass or any other magnetic material is around there. That was Faraday's big insight, that this thing called the field, it's not just a picture, or I suppose this was found out later, but the real insight was it's not just a picture, actually there is something there. And it was that insight that helped the development of physics in the 20th century. So what you could do is go on and do some deductions, but really you just want students to have that picture and be really, really clear what the field is. And yeah, the one extension task in the deliberate practice is for them to sketch what the field would look like for something like the sun. So I won't draw it here because you can see it in the slides. It's quite a simple picture. That's also really helpful though, because at some point they'll look at electric fields and the picture looks very, very similar. But the really important part here is to understand what the field is and this idea that it always shows the direction of the force at any given point. Hope that's helpful. In the next lesson, or in the next video, we'll be looking at the lesson on actually drawing this magnetic field pattern a bit more accurately. Thank you.